Hey, this is Brock Lemire's. We're continuing our study of embedded systems design, and we are now on to our next peripheral, which is the timer. And at this point, we kind of have a basic understanding of what a timer is, which is essentially a binary counter. But it's time to start looking at a specific timer system on the MSP430 FR2355. And in this video, what we're going to do is look at a specific timer, configuration settings that you can have, and prepare ourselves with all the knowledge that we will need to write our first program that will actually trigger an interrupt and do something when a timer overflow happens. So this video will not have a program example in it, but it's going to get all the background information for us so that we're ready to start coding. Okay, MSP430. It provides four main timer systems: timer A, timer B, real-time clock, and a watchdog counter. Okay. Now, each timer system within A and B can actually have multiple binary counters in it. Like timer B can have 4 separate counters. So it gives you just a ton of different counters within the system. Like I say, each one of the independent timers can generate its own interrupts. It can look for overflows. It can look for compare values, all sorts of different stuff. The key here, though, is that, remember, the MSP430 is the broad microcontroller family. And that's timer A and timer B, and each one has tons of different binary counters in it. When you down select your specific microcontroller, you got to look at which counter system was implemented, and within that, how many binary counters that you actually had. And so we are only going to look at the timer B system because our microcontroller only has timer B. It doesn't have timer A. And this is another source of confusion for other people other than us, because we understand how the documents work together. For example, if I come out to the user's guide and I see the family, I know that this monster data sheet is talking about the entire MSP430 FR4 and FR2 family, which covers tons of different microcontrollers. And I know that when I come out here, I see things like timer A and timer B listed as separate chapters. And yeah, that's fine. So this whole family could potentially have timer A and timer B, but it's only when I go to the device-specific data sheet that I start looking and seeing which of the timers are actually implemented on our system. So if I come over here, I start seeing things like, oh, peripherals. 3 16-bit timers are implemented, timer B3, one 16-bit, and I have it's called timer B7 for some reason. So it looks like I've got some timer B stuff going on. I come over to here and I look at the detailed description, and I come down into peripherals, and I look down here and I see, oh, there's my watchdog. That was implemented. Come down a little bit more. I see, oh, I see all this sort of stuff in here, and I'm looking for my timers. Here now is my timers, boom. And this is where I finally see that I only had the timer B system implemented, but it does have 4 separate binary counters. It's got a timer 0, timer 1, timer 2, and a timer 3, all within the timer B system. And we'll look at what the terminology is for that. So that's pretty cool. So from here on out, we're only talking timer B. But within timer B, we have 4 separate counters. You will see the abbreviations of them: TB0, TB1, TB2, and TB3. But each of these are totally independent 16-bit counters that we can configure. Okay, the terminology B3 and B7, where that comes from is you are going to have within each timer system these additional registers that are used to generate events. And timer 0 B3, for the B3 means that you have 3 of these different registers. They're called capture compare registers, and we're not talking about those right now. But this B3 means that there's 3 of those available within timer 0. Timer 1 also has 3 of them. Timer 2 also has 3 of them. Timer 3 has 7 of them. So that's the terminology. That's where you get this from. And so when you first see it, it is a little confusing because you see things like, I've got timer 0 B3. And you're like, what? Because I have a TB3 up here also, and then there's a B3, and it's a little confusing, but it's just the way it is. You just get used to looking at it. So when you see like this terminology, TB0, just 3 letters by itself, that's talking about timer system 0 within B, timer system 1 within B, timer system 2 within B, and timer system 3 within B. Then when you see the timer 0 underscore B3, that means it's describing some of the characteristics or capabilities that that specific timer has. And you usually notice it, like when I get confused, I usually try to look and see if you see a 7, because the 7, if I see a B7, I'm like, what is B7? There's no such thing as 7, timers within the system. And it's like, oh, I remember that has something to do with the characteristics of the timer. There's 7 additional registers that I can mess with. They're called capture compare registers, but right now I don't really care because I'm looking at overflows. Okay, here it is. Here is the big boy. This is the timer system that we have available to us. This block diagram is generic, meaning that it is what it looks like in all 4 of the timers. So timer B0, timer B1, timer B2, timer B3. They all look exactly like this, and they're all independent of each other. So here's what we have. Notice that we see a few things right away that are beyond our original understanding of a timer, which was a simple binary counter. Over here, I do see something that says timer, and I see 16-bit, and I see a clock, and then I see something else called TBXR. That must be the output, and indeed it is the output, and I see a clock. So this really is the binary counter. But it has a whole bunch of settings that allow us to set this thing up to get the desired capability or functionality that we want. I'm drawing this picture right here with this little box down here called timer overflow tracking. And that's because that's the first type of event that we're going to look at. As we look at more not advanced, but different capabilities and different event tracking, I'll start adding in more stuff in there. But for right now, we're just going to look at the simplest form of this counter, which is where we're going to set this thing up and let it run. And if it ever overflows, we will generate an event, okay? And that event is going to be an interrupt or set a flag. Okay. The clock input is critical to generating the time because we need to know the period of the clock to know how much time elapses per binary count. And so, what options do we have? The MSP430, the MCU we're using, actually gives us the ability to select 4 different clocks. TBX clock is actually a pin on the microcontroller. So if you go look at the data sheet, device specific, you'll see that one of the input pins is this. Okay, and of course it's shared with other things, but you can actually drive an external clock into here. Then there are 2 internally generated clocks that you can use. One of them is called A clock for auxiliary clock, and it has a 32 kilohertz clock. This is on the chip, so you get this for free. You don't have to wire anything up. The other one is called SM clock, and that is 1 megahertz. And so the S stands for, I think it's subsystem master clock. And these 2 are internal. And then you have the in clock. In clock is an interesting one because you have to go look at the data sheet because it's not always consistent what's hooked up here. Sometimes it'll be an external pin. Sometimes it'll be like another clock that's generated internally. But we know that the first 3 choices are really, we know those are always the same, and that's true. They are always the same. This one you have to go look up and see what they wired up on your microcontroller. But these 2 are what we're going to use because they're internal, and that's it. So we're either going to choose A clock or SM clock. Okay. We can also divide down the clock. And now, why would you ever want to divide the clock down? If I slow the clock down, it produces a slower count. And why would you ever want to do that? Well, the answer is that sometimes if you're trying to monitor time of like real world events, the real world runs a lot slower because the real world is full of humans. So things like trying to track time between button presses or time, like human time, like 1001, 1002, and tracking like minutes and days. You don't want you don't want a timer that's running at a megahertz, okay? Because the clock is running so much faster than the time that you're actually monitoring, it doesn't make sense. So there are applications where you want to slow this clock way, way, way down. And you do that by dividing the clock. And what dividing the clock means is if you had a 1 megahertz clock and you divided it by 2, that means you're going to have a 2 megahertz clock. Okay? And if you divided it by 4, you'd have I totally said that wrong. That would be speeding it up. If you divided the clock by 2, you'd have a half a megahertz clock or a 500 kilohertz clock. If you divide by 4, you'd have a 250 kilohertz clock if you divided 1 megahertz. Now, there's 2 divider stages here, and you can divide this thing way down. The first stage can divide by 1, 2, 4, or 8, and you select that by configuring these bits called ID, and these are just bits within a configuration register. Then you can also have another stage that can divide 1 through 8. So like 1, 2, 3, 4, 5, 6, 7, 8. And those are other bits within a configuration register. And so the combination of these 2 dividers is you can actually divide, you can have something like 32 different divider settings because you have 4 here and 8 here. So you have 32 settings, and you can get anywhere from a minimum divider of 1, which means you don't do anything to it. You just either pass 1 megahertz or 32 kilohertz, or you can divide it down by 64. So if you divided a clock by 64, you're getting really, really slow there. Okay, so you're I mean, that's like 512 hertz. I mean, that's really slow. I mean, 1 divided by 512. I mean, you're talking about a period of, in the milliseconds. Okay. Anyway, so you can divide the thing down. You can also, sometimes you want to speed the thing up. So how would I speed up the overflows? Well, overflows occur when the binary counter gets up to its maximum value and rolls over. So a 16-bit timer is going to have 2 to the n counts. So if you wanted it to speed up, one of the things you could do is use a smaller counter, because 2 to the 16 means you're going to have like 65,000 counts before it rolls over. But if you had an 8-bit counter, that would only roll over every 2 to the 8 or 256 counts. So if you shorten the length of the counter, it actually will overflow very rapidly. So just like these dividers slow the clock down in order to get a really slow overflow, you can change the length of the timer or the binary counter to speed up the overflows. So when you're trying to go faster, you wouldn't divide the clocks, you just shorten this. And you can use these bits called the control bits, and you have 4 different settings. The default is 16, but you can also get an 8, 10, or 12-bit counter, okay? Okay, then here comes an important one, the counting mode. So you can put the timer in different modes, and depending on what mode you have it in, it enables various things. When you put it in continuous counting mode, that means it's going to run forever. That means it runs up to its maximum value, rolls over, and then continues to count. That is the mode which supports generating an interrupt or setting the flag when you have an overflow. It only works in continuous mode. So since we're looking at overflows, that's the only mode that we care about right now for this section 12.2. And so it's important to put it in continuous mode. It actually is not in this mode to begin with. The other modes are up, where it'll actually count up, and then that's used for a different type of event called a compare. We're not looking at that right now. And then you have an up down, and that's used for something that I've never used it for, so I'm not going to talk about that. But anyway, so we are going to put it in continuous mode, and because that's the mode that just rolls over and over and over. When you go to set this up, you will notice that there's a clear button here. Or a clear bit. When you clear that, it actually clears everything in the counter, including the counter length and mode control, and it just gives you a fresh start. And so the recommended steps to configuring this is you write a 1 to this bit, which is TB clear, and it's in a configuration register, so you just do a bit set, and that will clear the timer out. It'll clear the timer, set the timer output value back to 0, it'll clear the states and the mode control, and then you go in and you configure the timer system. So you do saying, choose which clock you're going to use, choose which divider you're going to use for the first stage, choose which divider for the second stage, choose the counter length, choose the mode, and then if you want to use an interrupt, set up the interrupt, okay? This is where it becomes important to think about what the default values are for these. For example, the default value for these dividers is 1. So if I don't need to divide the clock, I just leave it at its default value. The default value for counter length is 16. So I usually leave the counter length and the dividers as is unless I know I need to change them, and I just use the default values. But mode control and the clock select, they default to values that aren't being driven. So for example, unless you drove a pin to this TBX clock, you're not going to get a clock. So you have to set up the clock select, and you have to change the mode because the first mode it's in is actually stop, so it's not running, okay? All right, let's look at where all these bits are. You get yourself this thing called the timer B control register, TBXCTL. The X stands for the number of the timer. So in this timer B system that we have, it's TB0 control, TB1 control, TB2 control, and TB3 control. And I drew this table up for you, which is just straight out of the data sheet. This is straight out of the data sheet. But this shows you all the different settings that you have. And some of these you see, like control. We talked about that. That's the counter length. TB select. That's a biggie. That's where we select the clock. ID. That's a good one. Mode control. We need that one. And then here's TB clear. But there's also some other stuff that we haven't talked about and we won't talk about. What I want to try to get you to the point is I'm going to get you to a state where you can do basic stuff, just the bare bones to get the thing running, and then leave you with the knowledge that if you want to explore the more advanced concepts of this timer system or any peripheral, you go into the data sheets, either the family or the device specific. But this is our buddy right here. This is going to be a lot of control bits are in here. The other one that you have is the timer B expansion register 0. And the 0 does not mean timer 0. It is just expansion register 0. That's just the name of it. That's all there is. But this is where you set the IDEX bits, which is the second stage divider. So you can see that this is the one that divides from 1 up to 8 and provides all the values. Okay, once we configure up the clock to know the period of the clock and the length of this, we can determine how often it's going to overflow. What happens when it overflows? We can use this circuit down here, which tracks when there's overflows to generate an interrupt. When it overflows, it's going to trigger a flag. It's going to set a flag, and the flag is called TBIFG. Where's that at? Well, it's in the TBX control register. If I go back, it's down here. There it is. It's bit 0, TBIFG. All right, that's kind of neat. So that's where I would see it. Remember, every time it overflows, it sets that. So if you're going to have an interrupt service routine that does something based on overflow, you got to clear that little buddy every time. What is the local enable for this interrupt? Well, I'll tell you right now, this is a maskable interrupt because it's a peripheral. So it's going to have a local enable, and that's the TBIE bit, timer B interrupt enable bit in the same control register. I come back here, you're like TBIE is bit 1. And that's how you do the local enable. So you have to assert that. This is a maskable interrupt, so the global enable is the GIE bit in the status register. Here is something that is interesting. When you look at this, notice that this TBIE and TBIFG, these bit names, they don't say, I'm the local enable for timer 0 in the B timer system. They don't say, TB0, TBIE. The reason is because this register itself is the name of this tells you which of the timers you're using. So if I set bit 1 in TB0 CTL, I'm enabling the local enable in timer B0. If I set that same bit in TB3 CTL, I'm enabling that local enable in the timer B3 system. The reason that's cool is because these masks, these bit definitions that I'm going to use, I can use the same one across all the different timer systems because this register has the same bit positioning. Okay, so now we set up that thing, we set up the time, we enable the interrupts, and now what happens when the interrupt happens? We need to write an interrupt service routine. Which vector do we need to initialize? If you look at this, you'll notice that there's actually 2 vectors for timer 0, B3. we got to look at the individual flags. Notice that this is the one we want, TB0IFG. That means overflow, okay? These other ones have this thing called CCR. That stands for capture compare register. Those are different interrupts, and they actually have their own flag. They have the capture compare interrupt flag G1 and G2 and G0. And so all you need to know is that this is the flag that we're using. And it's like, how'd you know that? And it's like, you read through the data sheet, but I'll just tell you, that's the buddy we're using. And I needed to know I'm in timer 0. I don't need to worry about the B3 or B7 because I'm just in timer 0, but that's the one. And that's important because notice that I need to use int 42 as my section name in order to initialize the vector address FFF6. Oh, all right, that is a lot of information about timers, but it is giving us everything that we need to actually write our first program to trigger an interrupt upon a timer overflow. That's it. As always, remember to support my channel by subscribing, and see ya.